In a similar way to question 7a, dealing with intervals of increase and decrease, question 8 deals with intervals of concavity. And so that requires the second derivative. So you can see the first derivative here using the power rule, bringing the 4 around front, canceling with the 4 in the 12, leaving a 3 in the denominator, and 4 minus 1 being 3. And the 3 coming around front, canceling with the 3 in the denominator here, and 3 minus 1 being 2, so that leaves 2x squared as that term. Then the second derivative is 3 multiplied around front, canceling with the 3 in the denominator. This negative sign remains, and 3 minus 1 is 2, so this term differentiates to negative x squared. Then 2 multiplied around front times 2 is 4, and 2 minus 1 is 1, so the second term, this term differentiated is 4x. Now, to find the critical points for change in concavity, or intervals of concavity, we set the second derivative equal to 0. So 0 equals negative x squared plus 4x. If you factor a positive x out, that will leave you with a negative x plus 4, which I have just turned around. I've just changed the direction here. And you solve this equation. You set each factor equal to 0, and so you see that the critical values are x equals 0 and x equals 4. X equals 4. And now I choose, and I've indicated those on this number line here, and I choose negative 1 in this interval to test, and I substitute that into the second derivative because we are dealing with concavity. So we have an x here, we put a set of parentheses and put the negative 1 in. We have an x here, put a set of parentheses, put the negative 1 in. And so negative 1 squared is positive 1, but it's negative, and so that's negative 1. 4 times negative 1 is negative 4, so negative 4 minus 4 is negative 5. That means that on this entire interval, from negative infinity all the way to 0, but not including 0, excuse me, the second derivative is negative, and so we move on to the next one, the next interval. And in this interval, I chose 1, what could be simpler than 1. 1 squared is 1, but it's negative 1. 4 times 1 is 4. Negative 1 plus 4 is positive 3. So on this entire interval, the second derivative is positive. And then finally, to the right, or greater than 4, 5 seems like the easiest value to substitute in here. So I put 5 in the parentheses here and here. 5 squared is 25. 2 times 5 is 10. So negative 25 plus 10 is negative 15. And so on the entire interval from 4, just infinitesimally far to the right of 4, all the way to infinity, the second derivative is negative. So from negative infinity to 0, from negative infinity to 0, and 4 to infinity, not including, that's what these curved parentheses mean, not including 0, not including 4, because the second derivative is 0 there. The function is concave down. So the function is concave down from negative infinity to 0, and from 4 to positive infinity. Then, because the second derivative is positive from 0 to 4, positive on the interval 0 to 4, the function is concave up on that interval. So there are the intervals on concavity, and we are also asked to identify all of the inflection points, just as we were asked to identify local extrema in question 7. Excuse me. Now, because the second derivative changes sign at both 0 and 4, so from negative to positive and from positive to negative, that means we have inflection points there. at 0 and at 4. So now we evaluate the function, not the derivative, not the second derivative. We evaluate the function to find out what the function value or y value of this x is, so we can determine both coordinates of the point. So we substitute a 0 in wherever we've got an x to the fourth. We put a set of parentheses, put the 0 in there, and we had an x here, so we put parentheses, put the 0 in there, and so that's just 0 over 12 and 0 over 3, and that adds up to 0. Now the second inflection point occurs at x equals 4, so I put a 4 in to the parentheses here, and 4 to the fourth is 64. It's negative, or actually it's not 64, it's 256. Yes, 256. And negative 256 over 12 reduces to negative 64 over 3. 4 cubed times 2 is 128, and so that's 128 over 3. Negative 64 over 3 plus 128 over 3 is positive 64 over 3, which is 21 and a third, or 21.333, and the line indicates again that this never terminates. It keeps repeating to infinity. So that makes our inflection points 0, f of 0, which is 0, 0, and 4, f of 4, which is 4 and 64 thirds, or 4 and 21.3333, never terminating. Okay, question 9 gave us information about the function. Excuse me. Sorry. Question 9 gave us information about the first and second derivative of this function here, and so we're supposed to sketch a graph based on that information. Now we are not going to plot the y-intercept because it's way down here out of sight, but we will need to plot the x-intercepts, which are the zeros, as well as any local extrema and any inflection points. And so we see that from looking at this factor, 1 minus 1 is 0, 0 times anything is 0, so that makes the function 0 at that point, so we plot that point there. And then we see from this factor, 4 minus 4 is 0, 0 squared is 0, times anything is 0, so the function value is 0. So we can tell by these factors that we have zeros of the function, or x-intercepts, at 1 and 4. Then we see that the derivative, first derivative, changes from positive to negative at x equals 2. And so that means that we have a local maximum there. And so when we substitute 2 into the function here, and I'm sorry I didn't put the calculations out here, but when we substitute 2 into the function here, 2 minus 1 is 1, 2 minus 4 then is negative 2, and negative 2 squared is 4, so that local minimum is x is 2, y is 4. And then the last thing we're looking at is the inflection point, and since the second derivative changes from negative to positive at 3, x is 3, then we have an inflection point where x is 3. Well, 3 minus 1 is 2. 3 minus 4 is negative 1. Negative 1 squared is 1, and so that's 1 times 2. So our inflection point is 3, 2. Now we know that the first derivative is positive from negative infinity to 2. So that means that the function is increasing, it's climbing from negative infinity to 2. And it makes sense because here's our local maximum. Then the function is, or the first derivative is negative from 2 to 4. So that means the function is decreasing from 2 to 4. And so we sketch a curve here and down through the inflection point and then down to the 0, the intercept at 4. And then yes, did I mention since the first derivative is positive from 4 to infinity, then the function climbs from, it increases from 4 to infinity. At 4 to infinity, that direction. And then here, at this point, the concavity changes. That is kind of hard to see, but we see that the function is concave down here, and the function's concave up here, and that's the spot where that concavity changes. So we have a nice graph here, especially since it's computer generated.